Hello everyone and welcome back to the channel. In today's video, we are going to train DETECTRON2 custom object detection and custom instance segmentation models. Let's get started. We'll pick up from our last video where we developed custom dataset for object detection and instance segmentation. If you have not followed that tutorial, the link is in the description. I also assume that you have built and installed DETECTRON2 on your system. If not, follow this tutorial to set it up on local computer and this tutorial to set it up on Colab. Today's custom object detection and custom instance segmentation code is compatible for Windows, Linux and Colab alike. Alright, you should have this dataset ready. In train and test folders we have images, and in train.json and test.json we have corresponding labels. Okay, so let's head back to Visual Studio Code. So I'm going to create 3 files. So first one is going to be train.py and second one is going to be test.py, and I also like to separate out all the utilities and helping functions in a separate file. So let's create another file called utils.py. Okay, so let's first start with train.py script. So let's first of all import setup logger. So from detectron2.utils logger import setup logger, and let's initialize it, setup logger. That's it. So next step, we have to register the dataset with DETECTRON2. So for that, let's import from DETECTRON2 datasets, and we should import register Coco instances, this one. Okay. And we also need default trainer to train the custom object detection and custom instance segmentation models. So let's import that from detectron2.engine import default trainer. And then we need some other libraries. So let's import OS and import pickle. Okay, so that would be it for all the libraries. So now let's define the paths to our configuration files and our pre-trained model files for object detection. So first we are going to do custom object detection, and in the second half of the video we will be doing custom instance segmentation. So let's start by config file path. And for configuration file path for object detection, we have to go back to DETECTRON2 model zoo. Let's go to object detection section, and here we can see that there are many models that we can use. There is always a trade-off between these models. So some models have a higher performance but it's also slower, and some have higher speed but those have lower accuracy. Let's choose this one, R50 FPN3X. So this is faster RCNN model for object detection. So let's copy the link, come back to our code and let's paste it here. So we only need this part after coco-detection. So rest of the URL we can just remove that. Okay, so this is our config file path, and for our checkpoint URL that has our pre-trained model checkpoint. So we are just gonna go with the same path. Okay, so next up we have to define where we want to save our custom object detection model. So let's define output dir. So that should be, let's call it output and /object detection. Okay. In our dataset we have just one class, so we also need to define how many classes do we have in our dataset. So we just have one class, so let's define a variable called num classes and it's equals to 1. So let's call it num classes. Okay. We also need to define where we want to train our models. So do we want to use CUDA or do we want to just train on CPU? So if you have CUDA enabled GPU, you should always go with CUDA. And if not, you can also use CPU. So now we also need to give names to our dataset. So let's call our train underscore dataset name. It's license plate detection model. So let's call it LP underscore train. And for our train images path, these images are here in our train folder. So I'm just gonna give that path. So train images path equals to train. And we also need to define the annotations path, which is this file train.json. So let's define another variable, train underscore json underscore annotate path, and this is this file train.json. Okay, so we have to define all these three variables for test split as well. So let's call test underscore dataset underscore name. It's let's call it LP underscore test, and test underscore images underscore path, it's this folder over here. So let's call it just test, and we also need annotation file. So test json annotate path, it's this file test.json. So let's put that here, test.json. Okay, so now we have defined all the paths. So now we need to register our data set, both the train and test, with DETECTRON2. So for that, we already have imported this register Cocoa instances module. So we can just call that and register our data set. So how to do that? So let me put some marker here. Okay. So let's call this register Cocoa instances. So first of all, we need to define what name we are going to give to this particular data that we are registering. So we already have defined that over here. So we are going to use that. So let's give name equals train dataset name. And then we also need to define metadata, but we'll leave that empty. After that, the path to our annotation file. So let's call that JSON file equals, it's already defined, train JSON image path, annotation path, so this one. And then we also need to define where all the images are for our train data set. So these are in our train images path, this one. So this way our train data set is registered, and we also need to do the same for our test data as well. So let me do that very quickly. Okay, great. So we have registered our train data set as well as our test data set, and let's run this and see if we have made any mistake. No, we haven't. Okay, so our data set is registered, but we also need to verify whether or not our annotations are correctly picked up by DETECTRON2. So for that, we'll write a function inside utils.py. So let's import dataset catalog and metadata catalog from detectron.data, and we need to import dataset catalog and metadata catalog. Okay. And we also need visualizer so that we can visualize all the annotations and all the predictions. So for that, from detectron2.utils visualizer, import visualizer. And we also need get config method to load the configuration for object detection model. So for that, let's import from detectron2.config and import get CFG. And we need model zoo as well so that we can load pre-trained model checkpoints for object detection. So from detectron2 import model zoo. And finally, we also need the color modes from detectron2.utils.visualizer import color mode. And now we also need some other libraries to load the images and to plot the images. So let's import random and also import CV2 and finally import pyplot. So from matplotlib.pyplot as PLT. Okay. So now let's define a function that will take the dataset name that we have given here, and then it will load the dataset from DETECTRON2, and then randomly we'll plot some images so that we can verify that our annotations are correctly registered with DETECTRON2. So let's define a function called plot_samples, and it will take dataset name as input, and it will also take how many images we want to plot. Okay, let's define that to be one image. Okay, so dataset underscore custom, that would be loaded from our dataset catalog. So let's call dataset catalog, and it's a dictionary, so let's call .get and then whatever dataset name that we have. Okay, and then we also need to get the metadata. So it's although empty, but we should follow this convention. So dataset custom underscore metadata, this should be equal to metadata catalog, and we'll get this metadata again against this dataset name that we are going to pass to this method. Okay, so now we need to plot the images, and for that let's run a loop. So for s in, let's randomly draw some samples, random.sample, and we are gonna get the samples from this custom dataset that we have just loaded. So dataset underscore custom, and we are gonna go for n samples, and for each sample let's load the particular image. So img equals cv2.imread, and we are going to get the file name from s, so it's going to be file underscore name. This image will be loaded, and then we are going to initialize our visualizer. So v equals visualizer, and we'll pass that image to this visualizer. But this image is loaded by OpenCV, and OpenCV loads the image in BGR format, but DETECTRON2 expects the images in RGB format. So let's just swap red and blue channels. So all images, all rows out columns, and last one will be swapped. Okay. And then we need to give this visualizer our metadata, so which is empty. We can still give it metadata dataset custom metadata, and finally we can scale up the images. Maybe let's do that with 0.5. Okay, now we can draw the annotations on this particular image. So we're gonna call v.draw underscore dataset dictionary. Okay, this one. Let's now plot it into a figure. So plt.figure, and let's give it a size of 20 cross 15, or maybe 15 cross 20. Okay, 15 cross 20, and plt.imshow, and we're going to get the image from our visualizer, v.getImage, and getImage is a function, so let's do that. And finally we are going to show that figure, plt.show. Okay, so now let's call this function on our dataset and verify whether we have correctly registered our dataset or not. So I'm gonna go back to train.py, and let's import everything from utils.py. Import static, so that means everything in utils.py. So from utils import static, and now we can call this function that we just created, plot samples, and we are gonna give it train dataset. So dataset name would be train dataset name, and we are just gonna plot how many images. Let's call 2 images. Okay, so let's run this, and there we have it. So we have correctly registered our dataset with DETECTRON2. So let's close this. All right, so let's get back to our code. So I'm gonna comment this because we do not need to verify anymore. Now we need to define the configuration. So for that, I'm also going to define a function inside utils.py. So let's come back over here and define a function get train underscore CFG. So this function is gonna get all the paths that we have defined over here for this configuration and checkpoint and the dataset names, etc. We have missed one path, so that should be over here. So let's define that. We need to save this configuration to later use in test.py. So let's define path for that as well. So CFG underscore save underscore path, that should be equal to, let's call it od underscore CFG dot pickle. Okay, so OD stands for object detection, of course, and we already have imported pickle, so we are good to go. Okay, now let's come back to utils.py. So this function is gonna get the path to this config file, and then checkpoint URL, and then train dataset name, and then test dataset name, and number of classes, and device to use for training, and of course output dir where our final model will be saved. Let me just close this one so that we can see the whole line. Okay, now we need to initialize CFG from the default configuration. So CFG equals get CFG. So this will give us the default configuration for the model, and now we can modify it according to our data set. So CFG dot merge from file. So that's where we are gonna give it the configuration for the model that we are going to use, which is object detection in this case. So which we have defined over here, this one. Okay, so we are gonna pass this path here. So we can do that by calling model zoo and then get config file. Okay, and then pass this config file path. And now we also need to define the pre-trained model's weights. So for that, let's call cfg.model.weights. Make sure it's in caps. Model zoo dot get underscore checkpoint URL. This one, and then we are gonna pass checkpoint URL variable here. Now let's pass the train dataset name. So cfg dot datasets dot train equals train dataset name, and then comma, and same for test dataset. cfg dot datasets dot test equals test dataset name, comma. And during the training, to load the data, we can also define the number of workers. So more the workers, the quicker the data is going to be loaded, but it's also going to stress your CPU more. So I'm just gonna go with 2 workers. So cfg dot data loader dot num underscore workers. And now images per batch. So for that, cfg dot solver dot ims underscore per underscore batch. So I'm gonna just go with 2 images per batch. And now we can define a learning rate. So for that, cfg dot solver dot base underscore LR. Let's go with something really small. Let's go with 0.00025. And maximum iterations. So how many iterations we are gonna go with the training. So for that, cfg dot solver dot max underscore iter. Let's go with 1000 iterations. We can also reduce the learning rate during the training, but we are not going to do that. So let's define solver dot steps as an empty array. Okay, so this will not reduce the learning rate during the training. Now we also need to tell our model how many classes are there in our data set. We only have one class which we have defined in this parameter, so we are gonna pass this parameter here. So let's define that. cfg dot model dot roi underscore heads dot underscore classes equals num underscore classes. And now we also need to tell on which device we want to train our model. So cfg dot model dot device, which is going to be this device that we have passed as parameter. And finally the output directory where custom object detection model will be saved. So cfg dot output underscore dir equals output dir. Okay. And finally we need to return this cfg that we have manually configured. So that's it for this method. Let's go back to train.py and come back over here. I'm again gonna put a marker over here. And finally, let's define the main function. So let's call this main and let's load the CFG. So CFG would be equal to get train CFG, this one, and we have to pass it configuration file path, then checkpoint URL, and then train dataset name, and then test dataset name, then number of classes, then device, and then output dir. Okay, now we are gonna get this CFG. We also need to save this CFG so that we can use it later in our test.py when we'll be running inferencing on images or videos. So for that, let's open a file with pickle. So CFG save path, we already have defined that above as write in binary. So let's call it f and pickle.dump CFG nf, and we can also define protocol, which should be highest protocol. So pickle.highest protocol here. So this will save our CFG, and now we need to make the directories where our output model will be saved. So we already have defined this directory over here, this one, output dir. So this directory is not there yet, so we can see here. So we do not have this directory, so we need to create that. So for that we can do this. So let's create os.makeDirs, and CFG, we can get this path from CFG because we already have defined that. So CFG dot output underscore dir, and if it exists then it's fine. Okay, it's true. And now we need to load default trainer. So let's call it trainer equals default trainer, and we have to pass this CFG to this trainer. So we are going to pass this custom CFG to this trainer, and we do not have to resume the training from any previous checkpoint. So let's set trainer dot resume or load to false, and that's it. Let's start the training. Trainer dot train. Okay, and now we have to call this main method. So let's define if name equals main. We're gonna call this main method. That's it. So let's run this and see if it works. Okay, our training has started, and from iteration 0, because we did not load any previous checkpoint. Okay, so we can see the total loss, and then classification loss, bounding box loss, and etc. We also see how much time is remaining and how much time is passed. So it's gonna take some time. So while it's running, we can continue with our test script. So let's head over to our test.py and start coding that. So it's going to be really small code. So from DETECTRON2.engine, we need default predictor. Import default predictor, and then we need to import OS, and we need to load this configuration file that we just saved. So we also need to import pickle, and from utils we need everything. Okay, so from utils import static. Okay, so cfg underscore save path. Now we need to load the cfg. So with open cfg save path, and as read binary as f, and cfg equals pickle.load from f. So this is going to give us the configuration file. So now for this configuration file, we need to load the weights that we have just trained on our custom object detection dataset. So let's redefine our model's weight path in CFG. So CFG dot model dot weights equals os dot path dot join, and we already have defined the output directory in this configuration file. So we are gonna extract that. So CFG dot output dir, and then our trainer will be saving our final model as model underscore final dot pth. So we have to give that file name here. So model underscore final dot pth. So it's gonna be there in our directory. So let's see what's there in our directory. So we have output folder, and in output folder we have object detection, and here we will see our model underscore final dot pth file when the training is done. Okay, so for now it's not there, but let's continue coding our test script. We also need to define the threshold for the detection. So for that, let's define cfg dot model dot roi dot underscore heads dot score underscore thresh underscore test. Let's give it 0.5. So any object that has a confidence of 0.5 will be displayed, and any object that is detected below this threshold will not be displayed. And now let's pass this CFG to our default predictor, and let's save it in predictor. Predictor equals default predictor, and give the CFG. Okay, so now our default predictor is gonna load our custom model that we are just training, and it's going to use our custom configuration file. And to run the custom object detection on the image, we have to define another function called onImage. So let's first call that over here, and then we'll define that in our utils.py file. So onImage, and it's gonna take image path as input, and it's also gonna take this predictor as well. So we have not defined image path, so let's define that. So image path is going to be something from test folder. Okay, test slash vehicle with license plate _37.jpg. So this is the image that I'm going to use to detect the license plate. And now come back to utils.py and define this onImage method. So it's going to be pretty much straightforward. So let's load the image using CV2, then get the output from the predictor, then pass the image to our visualizer, swap R and B channels, so all rows, all columns, and swap channel. Let's set the metadata equals none because we have not defined any metadata, and scale 0.5, and define the color as segmentation. Now let's draw all the instances on this image. So v equals v dot draw instance predictions, this one. From our outputs, get instances, and we are gonna give it to CPU. Finally, show this figure. So again, I'm gonna go with plt.figure, and fig size should be, let's go with 1410, plt.imshow, and v.getImage, and finally plt.show. It's going to show the predictions on image. So while the model is still training, so we can also define on video method as well, so that we can run the inferencing on the videos. I already have got two videos, highway.mp4 and street.mp4. So let's make it smaller and define another method called on video. It's going to take video path and predictor as parameters. So let's capture from the video using CV2. If capture is not successful, let's print an error and return from the method. Otherwise, we are gonna continue capturing it. So while we have the frames, so while success, we are gonna give the frame to our predictor and repeat everything that we have done over here. This time I'm going to use CV2 to show the results. So let's define a key press, and if we press Q, the video should quit, and otherwise we should keep on capturing the next frame from the video. So let's save this file, and looks like our model is about to train because we mentioned 1000 iterations and it's already 939 iterations. So let's define a video path over here. It's going to be inside test, and let's call highway.mp4, and we can call this on video method that we just created and give video path over here and predictor over here. So that's it. So yeah, it's about time that our model is fully trained. And if we go back to our folder, so inside this folder we can see that we have this model_final.pth file, this one. Okay, so now let's run it on this image and let's see. And here we have the results. So we can see that it is showing a bounding box and it is not showing us the segmentation mask because we have trained an object detection model and not this instance segmentation model. So in a moment, I'm going to show you how you can quickly train an instance segmentation model as well. So now let's see results of the video. So we can see that it is able to detect the license plates, but of course there are some false positives as well. So we just have like 50 images or so in the training data set, but still it's giving us good accuracy. But if you want a robust model, you have to increase your training data, or you should go for augmentation. Okay, so let's press Q here and get back to our code. So yeah, everything works as intended. So now let's train a custom instance segmentation model before that, let me show you what's inside this JSON file that we created as annotations. So let's open that. So you can see that for each image, we have its width and height and its file name. And against annotations, we have information about polygons of the segmentation mask. And we also have the bounding box. So bounding box is automatically inferred using min and max values in the X and Y axis. And if we are training an object detection model, only this information is used. If we are training a custom instance segmentation model, then this bounding box information as well as this segmentation information is used to train the model. So that's why we are able to train both the custom object detection model and the custom instance segmentation model, because in our annotations we have both of the information. So now let's quickly train instance segmentation model. So for that, head over to DETECTRON2 model zoo and scroll down to instance segmentation section and copy link to any model that you like and paste here for configuration file path and for checkpoint URL path. You need to remove everything before coco-segmentation and paste here. So I'm gonna do the same. So that's it. So now I do not want to save my custom instance segmentation model in the same folder. So I'm just gonna change this to instance segmentation. And we also need to change this CFG. So I'm gonna call it is_CFG. So this is for instance segmentation and the previous one was for object detection. So that's it. This is the only change that you need to make in our code. And now if you run this code, it is going to train a custom instance segmentation model. So let's run this. Our training has started. So it's gonna take a while. So I'll get back to you when this training is done. Alright, so it looks like our custom instance segmentation model is also trained. So if we go back to our folder, we can see that in output, we have now instance segmentation folder as well. And inside that, we have model_final.pth. We also have saved this is_cfg.pickle, which is for instance segmentation. And we already have this od_cfg.pickle. So now in our test.py, if we want to run object detection, we just need to use this configuration file od_cfg.pickle. And if we want to do instance segmentation, so let me just copy that and comment this. So if we want to do instance segmentation, we just need to use is_cfg.pickle. So that's it. So now if we run our test script, it's automatically gonna load instance segmentation model and it's going to give us the inferencing. We can see that now we have a bounding box as well as the segmentation mask. And on the video, we can again see the bounding box as well as the segmentation mask on all the license plates. So that's it for complete tutorial on custom object detection and custom instance segmentation using DETECTRON2. If you have learned anything of value today, hit like and subscribe to the channel, and I will see you in the next one.